Many programming languages force us to tackle multiple problems for every single problem we try to solve. First we build a feature and hopefully write tests for it. Then we usually try to make our code maintainable and beautiful. And after that, we often have to worry about performance. Is our code fast enough? Does it really scale? Can we rely on our code being consistent? Have we used the right language construct? And so on. These are some of the questions that bother us more the larger the scale we work at. But even on smaller scales, performance can still be important. Performance usually only becomes an issue, though, if we can reliably tell that we have a problem, which is why we should monitor our software closely to observe whether we have an issue at all. But when we observe such an issue, that usually means that we have to get back into our code to see how we can improve and optimize it to run faster. Many of the commonly used programming languages, however, don't support us a lot in this endeavor. We can always implement or use more efficient and effective algorithms, but we might also have to optimize our code in ways that hurt the readability and maintainability of our software. This is usually due to the fact that abstractions come at a cost. In some cases, we might even have to remove higher-level constructs and replace them with lower-level ones to get the boost in performance we need. Rust, however, mostly saves us from having to do that. It doesn't automatically choose the best data structure for us, but it makes use of a concept to try to spare us from having to fall back to low-level and hand-optimized code to get even the last bit of performance out of a hot path. That concept is called zero-cost abstraction, and we are going to take a look at what that is and a few of the things Rust has to offer in this regard. Before we look into Rust, however, we should probably take a look at the term zero-cost abstraction and understand what it actually means. The term itself consists of two parts, zero cost and abstraction, and we will start at the end and take a look at what an abstraction is first. An abstraction is a process of generalizing concrete details, or in other words, you take a lower level detail and then try to generalize it and make it easier to use and understand. As a simple example, we can take a look at a string. That string itself is just a sequence of bytes under the hood, and this already classifies it as an abstraction. It takes the lower-level concept of a byte sequence with a particular meaning, which in this case is that any byte or a fixed-sized group of bytes can be interpreted as a specific character, and abstracts it away into a structure that allows us to work with a string as a sequence of characters without having to worry about the underlying bytes too much. The other part of our term is zero cost, which usually means that there is no cost associated with whatever we refer to. In this particular case, however, zero cost is a little misleading, because there's always some cost associated with writing code. So what it actually refers to in the sense of our term zero cost abstraction is a form of abstraction that has no additional cost. Björn Stroustrup, the creator of C++, used better wording for this concept in his book, Foundations of C++. Zero overhead principle, which is a way more accurate description. If we now want to summarize what zero-cost abstractions are, especially in Rust, we can do it the following way. First, we don't pay for features we don't use, and second, the abstractions and concepts we use will mostly compile down to machine code that is as good as machine code that was compiled from lower-level code, including highly optimized code we've written ourselves. Overall, this means that we have higher-level concepts at hand that have the same runtime characteristics as lower-level concepts, without any overhead, which in return allows us to write more maintainable code without having to worry about performance implications. As the quote by Björn Stroustrup should already have shown, this concept isn't unique to Rust. It's also prominent and present in other languages, especially compiled ones like C++. But Rust definitely does its best to make good use of it. Oh, and that is also a pretty important statement we need to keep in mind, by the way. Rust does its best, which doesn't mean that it always succeeds in doing so. The process of optimizing code is pretty complex, and there are multiple parties involved. Rust-C, the Rust compiler, is actually only a compiler frontend for LLVM, which creates the actual machine code in the end. During compilation, Rust-C creates multiple intermediary representations of our code, doing quite a few things, which also involves optimizing code and passing as much information as possible to LLVM. After the result of this process is handed over to LLVM, the compiler backend also applies its own optimizations. All optimizations, however, need to follow certain rules, which state whether the compiler can or cannot apply these optimizations. For an estimated 95% of use cases, this is more than enough. And for the other 5%, we most likely have to perform a few optimizations ourselves, if the need ever arises. And finally, on top of Rust, C, and LLVM, the standard library offers data structures, algorithms, and abstractions that are already fine-tuned to work well for the majority of use cases. Understanding all this is important, because it explains relatively well that not all optimizations and zero-cost abstractions we will now take a look at work for every single use case. They just remain a best effort foundation, which ensures that we don't need to worry too much about our code. With that out of the way, let's look at Rust and what it does for us. One of the pillars of zero-cost abstractions in Rust are traits. They are Rust's version of interfaces in other languages, and thus a form of abstraction. These traits mainly do two things. First, they carry type information about methods, because they state what goes in, what comes out, and how any methods are named. And second, they form contracts, because if a struct implements a trait, it promises to fulfill the contract behind it. Rust even allows us to define new traits and implement them for already existing types. This basically gives Rust the power of extension methods, known from other programming languages. The only thing we need to do to activate such newly created methods on existing types is to import the corresponding trait into scope. After that, any new methods are callable for us as if they had always belonged to the type. Defining and implementing traits is really straightforward. We can define them by using the trait keyword and adding methods, declaring what goes in and what comes out. And we can implement them by creating an impl block, stating which trait we want to implement for which type, and after that, we implement all methods the trait demands. That's it. Consuming traits, however, is where a lot of the magic happens. The most common way to do so is through generics. In that case, we are not interested in any specific implementation, which is why we require a trait in the first place. The only thing we want is someone implementing one or multiple required methods, such that we can call them. This is done by requiring a generic type parameter to implement one or multiple traits. We can then call exactly the methods that are defined within the trait, and nothing else. The interesting part now is that Rust compiles away generics, which results in so-called static dispatch. That's the same thing C++ does with its templates. For every usage of a generic method with a concrete type, the compiler generates a specialized version. This process is called monomorphization. At runtime, this leads to a completely static call to one of the specialized versions of the method, and hence the name static dispatch. This process also comes with a pretty great advantage. It makes it easier for the compiler to decide whether to inline a function. In that case, all contents of a function are placed where the function call previously was. This duplicates code within the resulting binary and increases its size, but it saves a few instructions, potentially calling a routine, copying variables on the stack or into a register, and so on. Within hot paths of a program, inlining functions can reduce the time a routine or an algorithm takes significantly, for example. The more complex our use case becomes, the more efficient the whole static dispatching becomes, as the compiler always generates specific versions of all combinations of generics that are used within our own code. That's actually one of the zero-cost abstractions we wanted to talk about. We've used traits and generics to abstract away specifics of our domain logic, but at runtime, we get static method calls with specific types that are usually even optimized for exactly these types. For data structures that make use of traits and generics, for example, this means that data can possibly be laid out very efficiently for each individual type by the compiler, and each resulting specifically typed method can also be compiled down to the most efficient instructions, which brings the best performance possible for each individual type or combination of types. Most importantly, we aren't penalized for abstracting things away. We can use these concepts to make our own lives easier and code more generic and thus more widely usable, which is always an amazing accomplishment. Oh, and one more thing. Unlike in other languages, the usage of traits in Rust is fully type-checked once in advance, and not against each concrete version. which even saves some time when compiling. Interestingly, Rust doesn't even stop there, because it not only supports static, but also dynamic dispatch via opt-in. Sometimes we need some form of indirection at runtime and can't rely only on static information available at compile time. Listeners and event receivers are examples of that. Perhaps we want multiple of them, and not only one. And if we implement a small example like we usually would, we are left with exactly one type of implementer because generics don't allow for more. But we probably want to allow different implementations of our event receiver trait, all together in one vector, such that we can dynamically assign and call them at runtime. This, however, comes with a problem. Neither we nor the compiler knows the size of the concrete combinations of implementations at runtime, and thus can't reliably allocate space on the stack. That's where the opt-in comes in. We can effectively use our trait as a so-called trait object by boxing it or using it as a reference, putting it on the heap, and this then triggers the dynamic dispatch for us. Now the trait and its generic information are transported over to the runtime, and we pay the cost for it, but willingly, as we opted in ourselves. If we try to remember the beginning where we summarized what zero-cost abstractions are, this is the opposite of point 1 of our summary. We only pay for the features we use. In case of dynamic dispatch in Rust, we pay for the placement of our trait implementations on the heap. That is slower to access than the stack. And with the vtable the compiler has to create, which contains pointers to each specific implementation available. The generated code then checks that vtable at runtime and accesses it with the type it has at hand as the key. To then receive a pointer to a function it can delegate the actual call to. Another feature of Rust that uses traits as a foundation are closures. A closure is similar to a lambda function in Python or Java, or an arrow function in JavaScript. It's basically an anonymous function that can, unlike a normal function, also capture its environment. Whenever we define a closure, either directly as a function argument or by assigning it to a variable first, we have complete access to the surrounding context. This allows us to also access variables that are actually only available in the surrounding scope. Closures can also be used like normal functions and called with parentheses, because they are implemented in such a way that they allow for being used like any other function. Under the hood, these closures are backed by 3 important generic traits: fn, fn-once, and fn-mute. We need these 3 versions because they represent the 3 possible types of variable captures. Explaining completely how closures work is worth a video on its own though, so let's focus on the most important parts and go with a shorter, yet still correct version that just leaves out a lot of intermediary steps and explanations. Whenever the Rust compiler encounters a closure, it analyzes it, its captured variables, and its return type. Depending on how the captured variables are used within that closure, the compiler infers which traits still allow for the correct usage of these variables. When the compiler has finished its analysis, it implicitly creates a new struct and then implements each of the traits that can be implemented for that particular closure. The resulting type is transferred over to an associated type, and any captured variable becomes a member of that struct, together with its correct type. That means it is either stored as a reference, as a mutable reference, or as an owned value. The body of the closure becomes the implementation of the corresponding method, so either call once, or call mute, taking any closure argument as an argument of the method. This also explains why closures have backing traits that, of course, always have a self-argument. It's needed because the underlying generated struct holds the captured variables that need to be correctly accessed and used within the function body. The compiler can decide to implement one of 3 possible combinations of traits, which then decides in which places we can actually use that closure. First, only fn-once. Second, fn-mute and fn-once. And third, fn, fn-mute, and fn-once. In the resulting code, the closure is completely replaced by a struct initialization that takes all captured variables from the outer scope and a call to its corresponding method. The Rust compiler doesn't really generate any new Rust code, of course, but it generates the intermediate code that would result from doing exactly that. If we now take a step back again, we can realize what's going on here. We have generic traits implemented by structs with methods. The compiler will of course apply all the optimizations it can to this combination, which means that the generics are subject to monomorphization and thus vanish, and all methods potentially result in completely static calls to specialized functions, which in return are also easier to inline. So closures are also another instance of zero-cost abstractions in Rust. Oh, and we still deal with the same things we learned about earlier when looking at structs and generics. So we also have the option of an opt-in to dynamic dispatching by boxing our closures or using them as references. Once again, a feature we only have to pay for if we wish to. Now that we've talked about traits, generics and closures, which, as we know by now, are each a form of zero-cost abstraction, we should also talk about iterators that make use of them. Next to traditional loops like loop and while, Rust also supports iterator transforms. An iterator in Rust is a trait with a few methods, but its core consists of two things: an associated type that marks the type of items the iterator handles, and the method next, which advances the iterator to the next item in the collection. Any collection that wants to allow the iteration over its contents can implement the intoIterator trait that requires us to specify an associated type, which, like in the iterator trait, signals the type of the items, and the method intoIter that returns an iterator. This method is basically baked into the language. It allows us to use the higher level for-in loop, which automatically compiles down to code that uses a simple loop with match statements, effectively using the iterator's next method to advance the iterator and process the items until it's done with the last one. So once again, a zero-cost abstraction. intoIter itself iterates over T, consuming the collection and its items. This is why many collections also provide different iter methods to allow multiple ways of iterating. Other conventional methods are iter, which iterates over reference T, and itermute, which iterates over a mutable reference of T. The for-in loop, however, is not the most exciting part about iterators. If we take a look at the other methods an iterator provides, we can quickly spot quite a few functional methods that we probably already know from other languages. It contains the classic map and filter methods, but also more. Working with iterator transforms can often result in code that is better to maintain and easier to read than placing many statements inside a traditional loop. Additionally, it's also easier to add or remove a few statements in between, as each operation is a single function call with a closure as its argument. In many other languages, using techniques like iterators and functional methods come at a cost. But not in Rust. Generics profit from monomorphization, traits thus vanish, closures are compiled down to structs with methods that can be statically dispatched and thus often inlined, and so on. The iterator chain itself is also optimized by Rust, of course. In the end, Rust desugars all this syntax and basically creates code which in the end boils down to a simple loop that contains all the individual steps of the chain as statements within the loop's body, often also containing the directly inlined body of the closures. In other words, it doesn't matter whether we use a traditional loop or iterators to write our code. We usually end up with code that is at least as fast as handcrafted one. In some circumstances, using iterators can even be faster than using loops, because the compiler can apply even more optimizations because it has more information at hand, or because it can skip bounce checks or else. That, however, is not guaranteed. In summary, iterators are also a zero-cost abstraction in Rust, and they allow us to write our code involving collections in exactly those ways that suit us or our use case best, without having to worry about performance too much. There are quite a few more features in Rust that are zero-cost abstractions, but covering them all would be too much for this video. So let's focus on one more relatively important other feature of Rust that we should all probably use more often. Structs are an important feature of Rust. They allow us to group data and add common logic to it in the form of methods. This does, of course, come at a cost, because the struct somehow needs to be represented within a program's memory, with multiple addresses for all the properties. Single-field structs, however, can potentially be optimized, which can often come in pretty handy. Imagine we are working with time and want to represent durations. We can, of course, just use an integer to represent the amount of seconds that make up our duration. But that's not optimal, because an integer can literally be anything. Its type has no specific meaning. We can, however, create a single field struct with one property that holds our amount of seconds, and then add as many methods as we like, as long as we leave the struct at exactly one field. If we are then worried about the potential cost of the abstraction, we can point the compiler in the right direction by specifying a representation for our struct, transparent in this case. This leads to the compiler basically leaving out the struct completely. In the resulting machine code, the type has the same memory layout and ABI as the integer we've wrapped in the first place. The compiler can also apply this optimization itself, without defining an explicit representation, in theory. But that is often not guaranteed, so forcing it to do so often makes sense. If we now take a quick look at the fact that a struct method is actually just syntactic sugar for a function that takes our type as its first argument, and all other arguments after it, we can probably imagine that we pay basically no cost for our little trick. This technique can be applied anywhere else. Wherever we have a single property that we want to give more meaning and context to, we should wrap it in a struct. And if we are worried about the cost we could pay for it, we can simply tell the compiler to apply the transparent representation. That's all. If we now take a last step back and combine this knowledge about single field structs with our newly gained knowledge about closures, we can go one step further. Zero-sized structs, that are structs that don't even have a field or only fields that are also zero-sized, can also be optimized pretty easily. If there is no field at all, there's also no need for a struct at all. And this means that closures that don't capture their environment can often be compiled down to a simple static method call, and thus cost nothing more than a regular function call. We could probably go on and on and on and look at even more examples, but we've covered some of the most important ones now, and that shall be enough. But why again did we do all this? Well, we've gone through all of this to learn or remind us of one thing. Rust does its best to do as much for us as possible, and thanks to this, we don't need to worry about our code too much. We can write our code in the way that best suits us, our skill level, and our use case, and we don't need to constantly think about whether we've done the right thing. In some rare circumstances where we can reliably measure that we have a problem, we can jump in and try to optimize our code, but usually we don't have to. And this frees us to concentrate on the work that really matters: writing our code, completing features, and advancing our software. So, yeah, try to keep that in mind the next time something triggers you to think about whether what you've implemented will really work well. You usually don't have to. So, enjoy that feeling, and until then, see you in the next video.